Welcome back to Programming Fluency. This is section 9.2, Binary Input and Output. Last time you wrote text files full of readable characters, but text is wasteful. In this video, you will write the exact bytes from memory straight to disk and read them straight back with no conversion at all. Let's dive in. In the last video, you wrote text files full of human-readable characters, but text is wasteful. The number 1,000,000 takes 7 characters as text, yet it fits in just 4 bytes as a raw integer. Let's learn binary input and output. This is the plan for this video. First, text mode versus binary mode, and why binary data needs the modes RB and WB. Next, fwrite and fread. These copy raw bytes between memory and disk. Then struct serialization. You save and load a whole struct in one call. After that, file headers. You store a record count so the file describes itself. Finally, portability warnings. Byte order, padding, and the pointer field trap. Let's see the problem. When you write the number 1,000,000 with fprintf using %d, you write 7 characters. The digit 1 followed by 6 zeros. That is 7 bytes for a number that fits in only 4. And it gets worse. To read it back, you have to parse it. fscanf converts those 7 characters into an integer, 1 character at a time. Binary input and output skips all of that. Instead of writing text, you write the raw bytes the value already occupies in memory. The result is a smaller file, a faster read, and an exact copy of what was in RAM. This figure compares the two approaches for 5 integers. The text version, written with fprintf, stores each number as its digit characters, plus a new line separator. The binary version, written with fwrite, stores each integer as its 4 raw memory bytes, with no separators at all. Binary always reads back faster because there is no parsing step. The cost is readability. Open a binary file in a text editor and you see gibberish because the bytes do not spell printable characters. That is the trade-off. When you open a file with plain R or W, you get text mode. Text mode can translate certain characters. On Windows, it turns a new line into 2 characters, a carriage return plus a new line. That is harmless for text. But if you are writing raw bytes, and one of them happens to equal the new line value, text mode silently inserts an extra byte and corrupts your data. Binary mode disables all translation. What you write is exactly what lands on disk. You request it by adding the letter B to the mode string. RB, WB, a B on Linux and Mac OS, the two modes behave the same, but always write RB and WB anyway, so your code stays correct on Windows too. This is fwrite. It copies a block of bytes from memory straight to a file with no formatting at all. We have an array of 5 integers. We open numbers.bin in binary write mode, WB, and check for null. Then fwrite takes 4 arguments. First, the pointer to the data, which is the array. Second, the size of each element, size of int, which is 4 bytes. Third, the number of elements, 5. And fourth, the file pointer. Fwrite returns the number of elements it actually wrote, and we check it. The resulting file is exactly 5 times 4, which is 20 bytes. No new lines, no spaces, just the raw integers. Fread is the mirror of fwrite. It copies raw bytes from a file back into memory. We declare an array of 5 integers, open numbers.bin in binary read mode, RB, then call fread with the same 4 arguments. the buffer, the element size, the count, and the file pointer. The integers arrive in memory exactly as they were when fwrite wrote them, byte for byte, no conversion. fread returns the number of elements actually read, which may be fewer than you asked for if the file is short, and a single fread call loads the whole array in one operation. No loop, no parsing. That is why binary is fast. This is where binary really shines. You can save a whole struct as one block of bytes. The struct student has a name, an ID, and a GPA. We build an array of 3 students. We open the file with mode W plus B, so we can both write and read it. A single fwrite call saves all 3, using size of struct student as the element size. Because you cannot read a stream right after writing it, we call rewind to move back to the start, and then a single fread call loads all 3 back. The struct's fields and any padding the compiler inserted between them are all written as contiguous bytes. This is why fwrite needs the total size of the struct, not just the sum of the field sizes. One call out, one call back. This figure shows the round trip. The left block is the struct in memory, the main array, some padding, the ID, and the GPA. Fwrite copies that complete memory representation, 64 bytes here, straight to the file. On disk, it is just raw bytes with no field boundaries. Then fread copies those bytes back into an identically defined struct, and the exact layout is restored, including the padding. This works perfectly as long as you read it back on the same system, with the same compiler. There is one problem with a raw binary file. It is just bytes, so a program that opens it has no idea how many records are inside. The fix is to store the count at the very start of the file as a header. We open the file in binary write mode, then fwrite the count as a single integer. That is the header. Then we fwrite all the student records. Now the file layout is first a 4-byte count, then the records, one after another. When you read the file, you load the count first, and then you read exactly that many structs. The file describes itself. This is the matching loader. We open the file in binary read mode. Then fread pulls the count out of the header, and we check that it read exactly one integer. Now a defensive touch. We compute to read as the smaller of the file's count and the buffer's capacity max. If the file claims to hold 1,000 records but the buffer only holds 10, we read 10, not 1,000. That count less than max check stops a corrupted or malicious file from overflowing your buffer. There is an important limitation. Raw struct serialization is fast, but the files are not portable across different machines. 3 things cause this. First, byte order, also called endianness. A little endian system stores an integer one way, and a big endian system stores it the reverse way, so reading it back gives a wrong value. Second, struct padding. Different compilers may insert different amounts of padding between fields, so the fields do not line up. Third, type sizes. An int might be 4 bytes on one system and 2 on another. If your file only ever lives on one platform with the same compiler, none of this matters. That covers save files and local caches. But for data you share across platforms, use a text format like CSV or JSON, or serialize each field individually in a fixed order and size. Now 2 classic binary bugs. First, opening a binary file in text mode. Here we open data.bin with plain W, not WB on Windows. Any byte that equals the new line value gets turned into 2 bytes. That extra byte shifts everything after it, and the data is corrupted. The nasty part is that this works fine on Linux and Mac OS, where text and binary modes are identical. So the bug stays hidden until someone runs your program on Windows. The fix is simple. Always use WB for writing binary data and RB for reading it. The second bug is subtle and important. Writing a struct that contains a pointer field. In struct record, the name field is a char pointer, not an array. When you fwrite the struct, fwrite copies the struct's bytes, but name is just an 8-byte address. The actual string Alice lives somewhere else in memory, and it is not saved to the file at all. When you read the struct back, that address is meaningless, and using it is undefined behavior. The fix is to use a fixed size array, char name of 50, so the actual characters live inside the struct. Let's recap. Binary input and output writes raw bytes to disk and reads them back with no conversion. You open binary files with RB and WB, where the B disables newline translation. Fwrite and fread both take a pointer, an element size, a count, and a stream. Always check the return value to catch partial reads and writes. You can serialize a whole struct in one call, with its fields and padding written as a contiguous block. Adding a header, usually the record count, makes the file self-describing. But remember, these files are not portable because of byte order, padding, and type sizes, and never serialize a struct with pointer fields. Next, your file names are still hard-coded in the source. Real tools take file names and options from the command line. In the next video, you will meet argc and argv, the way a program receives its arguments.